Hello, we are students at the University of Texas at Tyler Houston Engineering Center, and this is a short presentation on cross-flow heat exchangers. We will be going over concepts, equations, and finally, an example problem.
There are many types of cross-flow heat exchangers. Many are used in applications such as gas-to-gas, gas-to-vapor, gas-to-liquid, and liquid-to-liquid heat exchange. Two examples of cross-flow heat exchangers are shown here. On the left, a fin tube heat exchanger in which tubes are pressed through thin metal fins, where the fins are used to increase heat transfer. The second example on the right is a cross-flow heat exchanger in which the metals are made into a shape similar to that of a sine wave. A mixed-unmixed heat exchanger, shown at the left, in which flow in the unmixed channel restricts lateral fluid motion, while the mixed flow allows the fluid particles the freedom to move about over the cross-section. On the right is a heat exchanger that has two unmixed regions, where flow is restricted in both regions. In this heat exchanger, the flow moves through a heat exchanger fashioned with flattened tubes.
The cross-flow heat exchangers have its own variation to its calculations. In this slide, we will show some of the equations used for cross-flow heat exchangers. Our first equation, 1018, is the Colburn modulus equation. This is a parameter to predicting the performance of these heat exchangers from empirical data. Equation 1019 is a Nusselt number that allows for finding the convection coefficient for the air side of the heat exchanger. The air side heat transfer coefficient is usually much smaller than that for the liquid side, so the contribution of the liquid coefficient to the overall heat transfer coefficient is negligible. Equation 1020, the friction factor. The friction factor for the air coefficient is also obtained from empirical data for cross-flow heat exchangers. Equation 1021, the heat transfer rate. The heat transfer rate is calculated by using an appropriate convection coefficient and calculating the overall heat transfer coefficient for the heat exchanger, where U is the overall heat transfer coefficient, A is the heat transfer area of the heat exchanger, F is a correction factor, and LMTD is the log mean temperature difference for counterflow. We can multiply these variables together to get the heat transfer rate for a cross-flow heat exchanger. Equation 1022 is the log mean temperature difference for counterflow. As indicated, we use the lowercase t to denote the cooler fluid, and the uppercase T refers to the warmer fluid temperature. 1 and 2 refer to the inlet and outlet, respectively. Equation 1023, capacitance ratio, R. This equation is the warmer inlet minus the warmer outlet all over the cooler outlet minus the cooler inlet temperatures. Equation 1024, temperature factor S. This equation is the cooler outlet minus the cooler inlet all over the warmer inlet minus the cooler inlet temperatures. Like in double pipe heat exchangers, the correction factor for cross-flow heat exchangers is a function of capacitance ratio R and temperature factor S. Figures 10, 11, and 1012 are the correction factor graphs for mixed, unmixed, and unmixed cross-flow heat exchangers, respectively. Obtaining the capacitance ratio R and temperature factor S, we can find the correction factor for any of these types of cross-flow heat exchangers.
In many cases of heat exchanger calculations, only the fluid inlet temperatures are known, and it is necessary to calculate outlet temperatures for the given heat exchanger. The effectiveness NTU method presented here is the most convenient way to calculate the temperatures. The effectiveness E is dependent on which of the two fluids has minimum capacitance, which is mass flow rate times specific heat product. The equations that are shown here are for separate cases of cold side and hot side being the minimum capacitance. If effectiveness is known for the heat exchanger, then equation 1026 may be utilized to find the heat transfer rate Q. Effectiveness equation can also be written in terms of number of transfer units N, which can be calculated in equation 1027. The ratio of capacitance C is defined by equation 1028. Figures 1013a 1013b and 1014 shows the effectiveness of the mixed, unmixed, and unmixed heat exchangers. Figures 1013a applies when the fluid with the minimum capacitance is mixed, while figure 10.13b applies when the minimum capacitance is unmixed. Figure 1014 shows unmixed heat exchanger effectiveness. Just like other heat exchangers, cross-flow exchangers suffer from fouling, but it is difficult to accurately apply fouling data. It is equally difficult to determine the pressure drop of the fluid streams that passes through the heat exchanger. Therefore, a minor loss of K equals 10 is assumed for each stream in these heat exchangers. The frontal area required for the airstream to transfer a required amount of energy is given in figure 1015. This graph is a result of calculations made on a number of heat exchangers.
The method of analysis for a closed-flow heat exchanger has been organized into a suggested order of performance calculations, which is now shown on the slide. From complete problem statement to the summary of information request, there are a total of 17 steps, but not all the steps are needed for each problem. By following the order of calculation, the closed-flow heat exchanger will be easier to analyze. In example 10.2, the water enters an unmixed type closed-flow heat exchanger at 200 degrees Fahrenheit with a flow rate of 0.7 pounds per hour, and the air used as cooling fluid enters at 70 degrees Fahrenheit with a flow rate of 2.5 pounds per hour. The frontal area is 2 square feet. The question is asking about the outlet temperature for both fluids. After reading the problem statement, we first discuss the solution of the problem, then state all assumptions for the problem, followed by nomenclature of all variables. Then we start solving the problem. Step A. Find out the fluid property at average temperature. For water, it's at 184.1 degrees Fahrenheit and air at 94 degrees Fahrenheit. Step B. Find the ratio of capacitance, which is 0.856. Step C. Find the UA product from the figure 10.15. When frontal area is 2 square feet, UA product is 1. Step D. Use the equation 10.28 to calculate the number of transfer units. Came out to be 1.665. Step E. Use figure 10.14 to estimate the effectiveness, which is around 0.494. Step F. Using equation 10.258 to solve the outlet temperature. The outlet temperature of the water came out to be 145 degrees Fahrenheit, and the outlet temperature of air came out to be 134 degrees Fahrenheit. Step G. Calculate the log mean temperature difference. And the last step, summary the information request. The outlet temperature of water is 145 degrees Fahrenheit, and the outlet temperature of air is 134 degrees Fahrenheit.
Lastly, we will address Chapter 9, Problem GP1. In this problem, a water-to-water, one-shell, two-pass heat exchanger is evaluated at varying lengths. The cold water enters the heat exchanger at 25 degrees Celsius, and the hot water enters the heat exchanger at 100 degrees Celsius. In order to save time, I will not discuss each individual calculation, but will instead show the calculated values on the screen. Feel free to pause the video if you need more time to review the values. A Microsoft Excel calculator was generated to determine the properties of the shell and tube heat exchanger. The detailed step-by-step analysis can be found on pages 466 to 471 in Jana's book Design of Fluid Thermal Systems, 4th edition. The assumptions made for the calculations were steady-state conditions, adiabatic heat exchanger, no fouling factors, along a streamline, incompressible fluid, viscid fluid, and hot fluid in the tubes. The properties for each fluid were evaluated at inlet temperatures. As can be seen by the graph, the difference between the outlet warm and cold temperatures get closer together as the length of the heat exchanger increases. This is due to the increased surface area allowing for more heat transfer to take place. However, this increased surface area due to the increasing length causes a larger pressure drop across both the inlet, along both the shell and tubes. Notice that the pressure drop across the tubes are more sensitive to the increase in length compared to the shell. Lastly, we have the heat transfer rate. The longer the heat exchanger, the larger the heat transfer rate. Notice that the increase in heat transfer rate is also not linear. This is because as the length of the heat exchanger increases, the temperature difference between the fluids decrease, leading to a lower increase in heat transfer rate.